Okay, Bismillahirrahmanirrahim. Okay, let's talk about isomerism a little bit first. So in the last class, a few participants told me the definition of isomerism. Can somebody recap real quick? What is isomerism? Or what are isomers? Yes. Come on, guys, participate.
Compounds with the same molecular formula but the different structural formula and
Very good.
different properties.
Very good. Yes. Different both physical and chemical properties. So that shows that physical and chemical properties are not only dependent upon the type of atom, but also their arrangement as well, right? And also another thing I want to tell everybody, I would like you guys to ask questions from me, okay? If there's any question popping up in your mind during my explanation or even otherwise, please go ahead and ask, okay? I don't like my students just sitting quiet and not responding and not asking questions. It feels as if it's like we are already online. I cannot have contact, eye contact with you. I cannot see your faces, you cannot see my face. So the only way we can make this more interactive and I want you to learn out of this, and the only way we can do that is by asking questions. If I don't know the answer of any question, no problem, we'll look into it. I'll look into it, you also go ahead and look into it, okay? We'll find the answers ourselves, but asking questions is very healthy. Okay, and I might be wrong. You can correct me. You can let me know that, I found this. And so discussions are healthy, and I learn and you learn, and that's the way it is, okay? Because I have observed in my last few classes that I don't get any response at all. No questions, no answers. And so it's kind of boring, So when students ask questions, it shows that they are thinking, they are learning, they're trying to learn. And so that makes me feel good, and that gives me satisfaction, a sense of satisfaction. Okay, so yes, isomers, Hala, good job, are molecules that have the same molecular formula, but different structural formula, and that is because the atoms are arranged in different ways. Okay. And so they have different physical as well as chemical properties. And now exactly how, we won't go into the details. The details are not included in IGCSE. The details are more in A levels. So when you'll go into A levels, you will see exactly how this works out. But for now, at least we will discuss how this isomerism affects the melting and the boiling points. So I talked about the melting and boiling points in my last class as well. Does anybody remember what we discussed? Okay. Like, for example, I gave this example. Let me see. For example, if I have these two molecules and now they are isomers, how do we know? Because if you count the number of carbon atoms, remember in the line diagrams, the ends of the lines and the corners, they are carbon atoms. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And when we don't show any atoms, it is understood that they are hydrogen atoms bonded to carbon. So it seems, and this is one molecule, okay? One line is one molecule. So I have shown 4 molecules here, whereas here I have shown only 1. So they are isomers. So which one is going to have a higher boiling point? And why? Sundas? Okay, Sundas is saying this one should have a higher boiling point. Why? Rita, loudly.
Because there's more interaction between the molecules, so like they
loudly. Yes, there's more interaction between the molecules, so more van der Waals forces between the molecules, and you can see how they can be stacked on top of each other, how they can be piled up, right? Whereas on the other hand, this is like a tetrahedron, and they cannot be stacked or piled on each other, because of which the molecules are going to be farther away from each other, because they cannot come too close. Are you getting my point? They cannot come too close to each other. I mean, just imagine tetrahedron boxes, You know what a tetrahedron, like it's a triangular pyramid, or yeah, triangular pyramids. And you cannot have pyramids, a lot of pyramids in a small space or stacked with the on each other. You will have a space in between them. So that is why. Okay. So when we have, so what does this show? There is branching. This is when you come across this. This means simple chain like this. This means simple chain like this. Simple chain of carbon with hydrogen atoms sticking out. No branching, no functional groups, no special functional groups, just a simple hydrocarbon. This line represents a simple hydrocarbon. What does this show? What does this show? If I make a structural formula, how will I make this? This will be something like this. So this is carbon. And so there are 3 more carbons. How will we name this? Let's try to name it. What do you think should be the name of this molecule? And these are all hydrogen atoms bonded. Will anybody try naming this molecule? We can be wrong. It's fine. I can be wrong. Okay.
Tetramethyl.
Okay. Tetramethyl, that's it. Is that a complete name?
Tetramethyl methane.
Okay. See, let me. There are a few rules. There are a few rules. I don't want you to go into too much details of naming the compounds, but a little bit is required. So let's just do as much as is required for now. So the first thing you will do when you are naming, first you have to find out, because you have to have a last name and first name. Okay, last name will depend upon what homologous series it belongs to, right? So we can see the bonds. The bonds are all single. There are no double bonds. There are no functional groups. So we know that this cannot be alkene. This cannot be, so this is maybe alkane, right? It looks like alkene. It's a simple hydrocarbon. So it's an alkane. So the suffix will be something ane, okay? And now, first of all, choose the longest carbon chain in the whole molecule. So starting from here, 1, 2, 3, starting from here, 1, 2, 3. Okay. So no matter which way we count, where the longest chain we can get in this molecule is having only 3 carbon atoms. So this is definitely propane. Okay, because remember the prefixes I did with you guys in the last class. For 1 is meth, for 2 is eth, and 3 is pro, and so on and so forth. So because the longest carbon chain has 3 carbon atoms, so I will use, and the suffix will be ane and propane. Okay, now I have to, the first name, if you have substituents, like if, for example, I'm taking this to be my parent carbon chain, like this is the main chain, which will decide its last name. So this is the parent chain. Now let's see, if this is the parent chain, then I have 2 groups attached. 2, and from where should I start counting? Anyway,
From any side.
Yeah, any side, because this is going to get 2 no matter from where I start. So this is going to be, okay, let's start from right side. 1, 2, 3. So I have 2 groups attached on the same carbon. So I'm going to write 2, 2 dimethyl. How did I do that? You didn't understand? Sundar is saying she didn't understand. Okay, but you understand the propane part, right? Okay, so now we have, the first part of the name, it either is going to, if it's a simple hydrocarbon, it's only, this is going to be the first part of the name, then it will only represent the number of carbon atoms, right? But because it has substituents, now what do you mean by substituents? Like Yes, like other groups are attached to the main chain. If you have things attached to the main chain. Now there are two. So let me write it in a simpler way. It's like this. Okay, and to keep things simple, I am omitting the H's. Well, okay, it is this. Same thing, but this was a twisted way. Okay, so I have two methyls. So I will write the name of the substituent. Because there are two, so I wrote di. Di is representing how many substituents you have. What happened to these two carbons?
Two.
Ask loudly, beta, so that they can also listen to your question. They will not participate in naming. We will not consider them in naming. Yeah, it's a parent chain, so I am counting them, but they will not be included in the final name, because only that carbon atom's number will be mentioned on which the substituents are attached. Okay, another thing, why did I write two twice? Because I want to tell that dimethyl, right? Both of them, both the methyls are attached on the same carbon and carbon. We will do more of this. We will do more of this. Okay, don't you worry. Let me give you another example. If I have this molecule, tell me the name of this. So before you name, first of all, tell me what family name, what first name.
Ethane as a family name.
Very good. Good job. Yes. Now substituents are?
Dibromine.
Yeah, okay. See, this bromine or bromo, whatever, is the first part of the name, right? So you cannot have "ene" here. Okay, do you understand? You cannot have "ene" here. This will be omitted.
Dibromoethane.
Very good job. Dibromoethane. Very good. So, yes. Also, okay. Another thing I forgot to mention. Yes, dibromoethane, and so
1.
Very good. And then dash. Remember, numbers are separated by commas, and number and letters are separated by a dash. Okay, so this is how we're going to write this. 1,1-dibromoethane. This is how. I took a class on how to name covalent compounds, covalent molecules. I took it last year of grade 6. And you can watch it. Some of the rules are the same. See, the naming of organic or covalent molecules is not the same as ionic. There's a little difference. Okay. We do not, like, in the name, we use these prefixes like di, tri, tetra. This we don't do with ionic compounds, but with covalent. I've taken a class. If you are interested, that will help you. If you know that, this is just adding on to the same. So family name, then substituents. You have to write the number of substituents, and then you have to write the numbers of the carbon atoms on which those substituents are attached. So this will be 1,1-dibromoethane. Now, why is this important? Why is it important to mention exactly and specifically where the substituent is attached? Because we have another isomer of this molecule, which is this. So we need to differentiate which one we are talking about. So they have the same molecular formula, but they have different attachments. What's the difference? Here, the bromine is attached to the same carbon. Here, bromine is attached to two different carbons. So this is, okay, let's name this. Yes, very good. So that's on this. Good job. Okay, let's name this.
1,2-dibromoethane.
Very good. Yes, this is what you get when alkenes react with bromine water. So this is what you get, but we will get to that later. Okay. Okay, so what I wanted to say is that more branching, less interaction between molecules, and therefore lower boiling and melting points. Okay, with that in knowledge, another thing. Okay, is there anything I'm missing out? No. I don't think
Miss,
so.
can I ask something?
Yes, yes, please go ahead. Yes.
If a question comes to make two isomers of the same alkane or alkene, so how can we tell two isomers?
You can see, it will depend upon what they give you. If there are functional groups attached, then change the position of the functional groups. Okay. If there are double bonds, change the position of the double bonds. Okay. And if it's a simple alkane and there are no functional groups and there are no double bonds, then show branching. Show branching like I just did. Like this was also isomers of butane, right? I just showed you. Okay. So there are many ways in which you can show isomerism. And by the way, in A levels, you have different types of isomers. You will have to study those. So, but for now, if they ask you to show isomers, you can change the attachment of the substituents. You can change the position of the double bonds. And if it's a simple hydrocarbon, you can show branching. Okay, but make sure you keep the number and type of atom the same so that the molecular formula stays the same. Okay, is there any other question?
Yes, Miss, I have one more question.
Yes.
And when we were naming the bromine one, why was the why was the ene removed?
Oh, okay. Why was the bromines ene removed? Because you see, it was, see, wait, let me get it. Yeah, here. Okay, see. Okay, when it is used as a last name, then you have this as a suffix. But here it was part of the first name. So, I mean, just look at the sound, bromine ethane. It's not sounding correct, bromoethane. Like it's actually ethane, but it has bromine attached to it. Are you getting my point? So like it belongs to the family of ethane. It is basically an ethane, but with two bromines attached to it. So the reason why we omitted ene is because this is a suffix when it is used as a last name. If it is a last name, then you can keep this ene. Okay, just like, no, that's not the example. So yeah, this is the reason. Is that
okay? Thank you, Miss.
Yes, because it's a part of the first name. You're welcome. Okay, now let's move on. Is there any other question? Okay, we'll do more of the numbering. Yes.
Miss, how can we know that how many isomers can a substance form?
That we cannot find out just like that. We have to know. I mean, they should exist in nature. You cannot just, I mean, in exams, if they ask you, you can come up with anything, but I mean, you cannot find the total number of isomers. That is beyond your level. Okay, because there are so many organic compounds, millions and millions of them. So, okay. Is there any other question? They won't ask you a question like that. Okay, is there any other question? Okay, should we move on? Yes. Yes.
This is getting a little confusing for me because the last classes I did not attend them. So this is getting a little bit too confusing for me, so you can imagine. So,
yeah, that's fine. Yeah, that's fine. I have recordings. Even if you don't understand, I mean, even this class is getting recorded. You can go back and watch that recording and then things will make sense. Don't worry. Okay.
Can I ask you one thing?
Sorry?
Can I ask you one more thing?
Yes, yes.
Where can I view your recordings?
On my YouTube channel.
Okay,
I have my
channel.
Are you in the group?
Excuse me?
Are you in my are you in my WhatsApp group? Because I share the recordings of my classes after after the class.
Maybe more.
Okay, if you're not, then please contact me. Okay, then I'll add you up and you can get the links. Okay.
Okay.
Okay. Okay, then let's move on to the chemical reactions, okay, of alkenes and alkenes. So we were talking about combustion. Combustion is the reaction of any substance with oxygen. Okay, combustion, the word combustion means reaction with oxygen. It is used for non-biological molecules. I mean, when the same process takes place inside our cells, inside our body, then it's called respiration. But otherwise, outside the body, it's called combustion. Okay, so it's very highly exothermic. And I said, why is it exothermic? Is because they make very stable carbon dioxide and water molecules. And because they are so stable, they are far down on the energy level diagram. And that is the reason why they are used as fuels, is because they release so much energy. So they are a very good fuel source. Okay. Now, can alkenes be used as fuels? Are alkenes used as fuels? Alkanes are, okay. But what about alkenes? Can alkenes be used? That's my question.
No,
Why not?
because the double bond breaks and it reacts with the oxygen, I guess.
So isn't that a good thing? I mean, and more energy should be released, right? Yeah, no, you are right. Yes. So alkenes are less stable, right? Because of the double bond. Is that what you're saying? So they are less stable, but the less stable meaning higher up on the energy level. So if anything is higher up above the level, when it undergoes the exothermic reaction, it will, on the net basis, I mean, it's making the same products. So it should be releasing more energy, right? Yeah. So do you think? Ask questions like that, okay? And you have internet to answer your questions. So go ahead and search if you cannot find the answer. See, the thing is that alkenes, first of all, can be used for energy sources, but they are preferably not, and alkanes are preferred instead. Reason being that alkenes are used for other purposes like plastic. Plastic is made up of alkenes, and polymerization. I mean, that's a different thing. So they are used for something else, not as fuel sources. Another reason is that when it combines with oxygen, it gives us unclean flame. Like its burning is sooty. You know what sooty is? Like some things burn flame. I mean, the flame is colorless. When something burns, it produces a flame, right? Now, if the flame is colorless, that means clean burning. No mess, no blackish, no black deposits, no soot. You know what soot is? Soot is simple carbon. Soot is simple carbon that did not get a chance to react with oxygen to form carbon dioxide. Okay, that is soot. So, you know, the blackish deposits that you see under the chimneys or in barbecues, that blackish deposit, what is that blackish deposit? That's soot. That carbon, that burned carbon that could not combine with oxygen. That's unclean. That's unclean. So why do we, so alkenes have this problem. So there's a equation here in your book. So when alkenes combine with oxygen, they just simply give carbon dioxide and water. Why is that? Because they burn cleanly and they give these harmless products, carbon dioxide and water. They're not pollutants. They're just normal constituents of air. And so this is clean and good. And also it's highly exothermic. Energy is released. And so they are good fuel sources without any pollution, right? On the other hand, this is an equation. Again, they have shown alkene here, not alkene. But if Even alkanes require ample of oxygen supply for all the carbon atoms to get converted into carbon dioxide. You have to have a lot of oxygen to make sure that all the carbon atoms get a chance to react with the oxygen to give you carbon dioxide. If there is inadequate oxygen supply for any reason, then that means some carbons will stay unreacted with oxygen and they will not be able to make carbon dioxide. I tried to make this structural, so like structural formula equation. So can you see all the carbon atoms need at least 2 oxygen atoms to bond with to form carbon dioxide. So for this, they need ample of oxygen supply. So alkanes, if are supplied with inadequate oxygen, can also give soot or carbon monoxide as well. Now, it all depends upon how much oxygen you are supplying. If you're supplying good oxygen, then all of them will combine to give you carbon dioxide and water. If there is little oxygen, but it's not adequate, then one carbon atom will manage to have only 1 oxygen atom. And that will give you carbon monoxide instead of carbon dioxide. And if, for example, the oxygen supply is too low, then you will have simple carbon, which is soot. Okay, I did not make an equation for that. So it depends upon the amount of oxygen. So basically what's happening here, carbon is reacting with oxygen to form carbon dioxide or carbon monoxide, right? Now, if you change either the supply of oxygen or the number of carbon atoms per mole, which require that oxygen to make carbon dioxide, that ratio of carbon reacting with oxygen will determine what product you're getting. Are you getting me? Or maybe I made it too complicated for you. For example, the alkene general formula is what? This, right? And the alkene general formula is this, right? So now look at the carbon to hydrogen ratio, or you can say which molecule has higher carbon to hydrogen ratio. Same number of carbon. Here, hydrogen is more. Here, hydrogen is 2 less, each molecule. So carbon to hydrogen. So carbon to hydrogen, if I write like this, so this, when this is more, this is less, right? And when this is less, the whole ratio will go up. Did you understand? So alkenes have more carbon to hydrogen ratio per molecule. That means there are more carbons required or waiting to bond with oxygen to form carbon dioxide. So for alkenes, if you want, with alkenes, if you want only carbon dioxide and oxygen, you want the flame to be clean, you don't want any soot, you don't want any carbon monoxide, that means you have to supply a lot of oxygen, even more than alkane, because per mole, per molecule, they have more carbon demanding to bond with oxygen to form carbon dioxide. That's why it's not possible all the time. Therefore, alkenes, instead, what they do is with oxygen, they make carbon monoxide. So they make more carbon monoxide and they make more soot. These are pollutants. That's why they are not used as fuel. Okay, then you will see a lot of pollution, a lot of things turning black. That's why alkenes, they are cleaner. So if you burn alkene in a laboratory, you will see that the flame is colorless. And if you burn an alkene in a laboratory, you will see black. You will see blackish.
Miss, I still didn't understand, like, how does the alkenes have a high ratio?
See, carbon to hydrogen ratio. Okay, you don't, if I will try my best to explain you, but don't get confused. I don't want to confuse you. What I'm trying to say is that why are alkenes not used as fuel is because it is more, meaning they require more oxygen. then alkenes to produce carbon dioxide and water. And these are clean products. I mean, alkenes can also undergo combustion, but then they are more likely to produce carbon and carbon monoxide, because see, you have to see per mole ratio. You have to see per mole ratio. Mole, don't be confused by mole. Okay, if mole is complicated for you to understand, look at molecule. Molecule, if you talk about one molecule at a molecular level, the ratio of carbon to hydrogen is more here. So there are more carbon atoms. Okay, but remember, hydrogen is less. And so hydrogen will also not that much available to produce water. So you don't have the normal products, but you have these pollutants. So that's the problem with alkene combustion. Okay, so I'm comparing alkenes and alkenes reaction with oxygen. Okay, look at this general formula. Each alkene molecule has 2 less hydrogen atoms for the same number of carbon atoms. Okay. Okay, and now
thank you.
I hope you understood. Okay, now look at this flame that they are showing in this picture. What they're showing is, when you see yellow color flame, this shows that there is incomplete combustion going on. Why? Because that means soot is being produced, unreacted, you can say carbon, or burned carbon, which did not react, which did not get a chance to react with oxygen. That carbon, when burns, gives you a yellow flame. Okay, that carbon, when it burns in flame, that gives you a yellow flame. Why is it called a safety flame? Is because if it's dark yellow color, we can see it, and so we can save ourselves from it, and we can, control it. It's easier to control. And so when, for example, you need to keep the Bunsen burner on and you don't have anything to heat, for example, for any reason, then this is the flame we use, and it's called safety flame, because you can easily protect yourself from it, because otherwise the normal flame is absolutely colorless. So, we don't know, and it can burn us, right? And we also don't know how higher the flame might get. And so it can cause accidents, right? So that's why it's called safety flame. Another thing, they have talked about carbon monoxide poisoning in here. Does anybody know anything about carbon monoxide poisoning? This is from biology. Yes, Hala? Yes, Hala?
The carbon monoxide, when it enters our body, it reacts with the hemoglobin of the red blood cells, and this decreases the transfer of the oxygen to our body.
Very good. Yes, yes. Yeah. And you will, I think, go, there are not much details in IGCSE, right? But in A levels, you'll do this in greater detail, this carbon monoxide poisoning. What happens is that hemoglobin, if you remember, picks up oxygen from the lungs, right? And then it delivers to the cells, and it does the opposite with carbon dioxide. It picks up carbon dioxide from these cells and releases them in the lungs, right? Now, what carbon monoxide does is that, see, these oxygen and carbon dioxide molecules are attaching to hemoglobin reversibly. Reversibly mean that they attach and then they detach according to the requirement. So at the point of lungs, oxygen attach. At the point of cells, oxygen detaches, and vice versa for carbon dioxide. But the problem with carbon monoxide is that when it attaches once, it does not detach. It does not detach. It attaches permanently. So that hemoglobin is gone. Now that hemoglobin is not available to attach to any, and it attaches exactly at the same site as the oxygen. So now oxygen's seat is taken away. Think of it as somebody sat on your seat and now it's not getting off. So there is no chance for you to now get on that vehicle or bus or whatever. So it does not detach, and so oxygen cannot sit on that hemoglobin anymore. And so when this goes on, this progresses on and on and on, all the hemoglobins are gone. And so now who will take oxygen to the cells, right? So that is where carbon monoxide poisoning, this is exactly what happens in carbon monoxide poisoning. And so yeah, cells die. So yeah, you can think of it as cells suffocation. Okay, so let's see. Okay, another thing they have mentioned here in this study tip is that you should be good at writing equations of these combustion reactions. Combustion reactions. So you should be good at writing combustion reactions. Let's try. Let's try a few. Let's start with simple methane, okay? Methane reacting with oxygen. So we know the reactants and we know the product. So let's just write down the reactants and the products first, and then we will balance. Now, the number one step that I would recommend when you are dealing with hydrocarbon equations, especially this combustion reaction, look at the first, balance the carbon atoms. Number one step, balance the carbon atoms. So 1, 1, balanced already. Second step, hydrogen. Okay, why not oxygen? Oxygen is all alone. We can deal with it later on. Leave it for the end. First carbon, then hydrogen. 4 here, 2 here. Okay, so let's balance the hydrogen first. Now 4 hydrogen here, 4 hydrogen here, that's fine. But what about oxygen? You will see that in most of the combustion reactions, you have an odd number of oxygen on the right-hand side. You will see this no matter what hydrocarbon. I mean, I don't know, but especially with alkenes and alkenes, you get an odd number of oxygen atom on the right side. Now 1, 2, 3, 4. Okay, this was, yeah, okay. So this one, this is not having an odd number. 1, 2, 3, 4. So this is easy. 1, 2, 3, 4. So there you go. Let's try with ethane, because I remember that happens. 2 2s are 4, 5, 6. So this is the formula for 6. Use the general formula if you don't remember the formula. Okay, write down carbon dioxide and then water. So first of all, carbon atom, 2 carbon atom. How many oxygen? 2 here, 6 here. 3 2s are 6. Okay, now how many oxygen atoms? 2 2s are 4, 5, 6, 7. 7. See, odd number. Now, how can we have 7 here? We have 2 here. So whatever number I write here, I'm going to get something even, right? So what to do? Now, how I do it with the way it is done is that now what you do is you want a number here, which when gets multiplied by 2 gives you 7, right? So in which number gets, so you're basically dividing 7 by 2. 7 divided by 2 is 3.5, right? 3.5. We cannot have 3.5 oxygen molecule. Now, in order to get rid of this decimal, in order to have all the coefficients as whole numbers, I multiply the whole equation by 2. Because it's 0.5, multiplying by 2 will give me a whole number. So now everything will get doubled up. So 2 ethane, and this will become 7. 7 oxygen, 4 carbon dioxide, 6 water. And now this is balanced. Okay, let's check. 2 2s are 4, 4. 2 6 are 12, 6 2s are 12. 7 2s are 14, 4 2s are 8, 9, 10, 11, 12, 13, 14. So 14 oxygen atoms on both sides. Okay, remember this, they're going to ask you, it was written here, you should know how to balance a combustion reaction of a hydrocarbon. Okay, this was complete combustion when you have only carbon dioxide and water as your products. What about incomplete combustion? Incomplete combustion, let's see. Okay, methane plus oxygen giving carbon monoxide and water as well. Okay. Again, carbon should be number 1 step. Okay, then hydrogen, 2 2s are 4, 4. Now what to do with the oxygen? 1 2 3, 1 2 3. So 1.5, right? Multiply the whole thing by 2.
Again, multiply by 2.
Yes. So 2, and then this becomes 2, and then this becomes 2. 2 2s are 4, H2O. So are we balanced? 2 carbon, 2 carbon, 2 4s are 8, 4 2s are 8, 2 2s are 4, 1.
Miss, 2
4,
into
5, 6.
1.5 gives us 3.
Oh, sorry, yes. Okay, sorry, yes. 3 2s are 6, so 2 and then 4 6. Okay, you got it? Okay, you can try with other alkenes. You can try with other alkanes, and we can even try with an alkene. You can go ahead and also try with alkene and see if you are getting but yes, in organic equations, you do get coefficients like that, you know, odd and even problem on the 2 sides. So come up with a decimal that will give you the same number, and then multiply the whole equation by 2 or any number that will give you a whole number. Okay. Okay.
Miss,
Yes.
do we also have to write the state symbols?
Yes, 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 the state symbols are important. So remember, these are usually gases. Oxygen is a gas, we know that. Carbon dioxide is a gas, carbon monoxide is a gas. And because this reaction is so exothermic, it releases so much energy, most of the things are in gaseous state. So this water is also in the form of steam. Okay, this will depend upon the molecular weight, of course, right? So which smallest alkene is a liquid at room temperature?
C5H12.
Right, good job. Yes, pentane. Pentane is the smallest. So how by looking at a table, how can you tell which alkene is a liquid at room temperature? By just looking at the table, if you did not have this column, just by looking at the table, how can you tell which alkene is a liquid? Sundar, what will you look for?
The boiling point will be more than 25 degrees Celsius.
Very good. And why do we use 25? Why
It's
do we use
the room temperature.
Right, it's the standard room temperature, right? So boiling point, if it is less than 25, sorry, more than 25, that means it is a liquid at room temperature, right? So pentane is the first one, the smallest alkene, which will be liquid. So making use of that information, you will put the state symbols in your equations, okay? Okay, let's see. Okay, then, so we discussed combustion, substitution reactions. Okay, before substitution reactions, yeah, I forgot this addition, this bromination, this addition reactions on this page 258. I forgot to mention this. Remember the identification test for unsaturation. What was the identification test for unsaturation?
Adding bromine water to the alkane or the alkene.
Very good. And then what happens?
The bromine water in presence of the alkene will turn from brown to colorless, and for the alkane, it will remain unchanged.
Okay, so why does that happen? What happens?
Because the double bond in the alkene, it breaks,
Right.
and it
Right,
reacts
very
with the
good.
bromine.
Yes, so this double bond, because you know both bonds are made of electrons, so similarly charged, and so they repel, and so one of them is unstable, and so the carbon now have one electron available for bonding, and so these bromine molecules, their bond also breaks. They come here and they attach themselves here, and so this becomes 1,2-dibromo ethane. Okay, can we have this molecule as a result? 1,1-dibromoethane. Can we have this as a result of this addition reaction?
No,
Why?
because one carbon only has one extra electron.
Okay, good job. Yes. Okay, good. So, sorry, open loudly, beta.
Because like this double bond would like snap open, like that's like not one carbon.
Yes, very good job. Yes, yes. But yes. Yes, another thing, there's another reason. Okay, you guys are also correct. Another reason. Remember, carbon. Okay, before I answer that question, before I give you another reason, answer this question. Why doesn't alkane react with bromine? Alkane. Why doesn't alkane react with bromine? What's the reason? Like if you have alkane, it will not react with bromine, right? That's the identification test. So if the bromine keeps it brown color, if it keeps its brown color, that means that all the bonds were single. So why is that? Yes, Yusra?
Because alkanes are stable.
Very good. Yes, yes, alkanes are stable. So basically these bonds are stable, right? These backbone, these carbon hydrogen bonds are really, really stable and strong, and you need to put in a lot of energy to break them. So this is not an exothermic reaction. This will be endothermic. I mean, you have to put in more energy. Okay. So, okay. So this was bromination addition reaction. Then they have also mentioned that we can also use acidified dilute solution of potassium permanganate to check for the unsaturation. How does that work? Any ideas? How does that work?
The solution turns from purple to colorless in presence of an alkene.
Very good. So why? What happens?
The alkene gets oxidized, I think.
Very
so.
good. Very good. Very good. It gets oxidized by, what's the oxidizing agent? Who is oxidizing it?
The potassium manganate.
Very good. Hala, good job. Yes. So potassium permanganate, remember, was a very strong oxidizing agent. And so again, this double bond snaps open, this breaks, okay, and then you have these electrons available for bonding. And so you have OH groups coming and attaching to them. So this becomes a diol. That's another homologous family. We're not going to deal with them, but just for your information, because you see, I don't want to go into unnecessary details. These things may not be examined, but the reason I discuss is because I don't want you to memorize, because memorization becomes tough and difficult. So if you know a little background, like why is this happening, if you're convinced, it helps. So yes, so this is oxidation. So you see that oxygen is directly bonded to the carbon atoms, okay? And then manganese, and then of course, we know from redox reactions, we have done redox reactions, that oxidizing agent itself gets reduced, right? When it is oxidizing the other reactant and it itself gets reduced. So here, manganese oxidation state is +7. If you calculate it, it's +7, and here it's +2. So you can see that it has reduced, okay? And carbon, by the way, so you can ask me that what about whose oxidation state has increased? So this is reduction, right? This is reduction. So you might ask me whose oxidation state might have increased. So it's carbon. Carbon's oxidation state has increased. Okay. I don't know what.
Miss?
Yes.
Miss, you said that the alkane doesn't react with the bromine, but then what was 1,2-dibromoethane?
Yeah, that was ethene reacting with bromine, not ethane. That was ethene. Are you getting confused by the fact that we name it as 1,2-dibromoethane? So we should be calling it ethene? Yeah, I understand your question. Yeah, so that was ethene. The reactant was ethene. Yeah.
How will the bromine attach to like one carbon? Because if it's always going to open up like that, then how did the bromine?
Like, how did we get this particular molecule? Yeah, so this molecule is not possible with this reaction. This particular, yeah, you guys are right. So this doesn't happen. Yeah, so, but we do have this, but it's not this reaction. We do get this, we do get it, but that's a different, that's a photochemical reaction. That's a substitution reaction. Okay, but not through this, because you see, this addition reaction is totally spontaneous. Like you don't have to heat or do anything, just mix. You know, like they have shown this picture, just mix. There is no heating or anything involved. Is it? What reactions are spontaneous? Spontaneous meaning you did not heat them, just mix and that happens. That's called a spontaneous reaction. What makes the reaction spontaneous? Yeah, well, what does it mean? How, why? They're exothermic. So the room temperature is enough. The room temperature is enough energy for them to start, and they release energy, in fact, yes. So there's less activation energy, right? So this is a spontaneous reaction. This also is possible, but this is not spontaneous. You will have to use photochemical reaction that we will come to later on. Okay. Hala, did your question get answered?
Yes.
Okay. Okay, so it's 7:23. We are getting late. Okay, so I couldn't move on too much. I wanted to do.
Miss,
Yes.
Miss, can you show the redox reaction again that you wrote?
Okay, that equation was not required. Okay, I just wanted to give you a little background on why this happens. Okay, do you want me to show you? But I don't want you to get confused.
No,
All
Miss,
I'm showing.
you said
all
that is reduction process, right? So
Yes.
reduction gain of electron. So it is coming from plus 7 to plus 2. So how
Right.
is it gaining electron?
So how is it gaining electrons? Is that your question? Yusra?
Yes, Miss, yes.
So your question is, how is manganese gaining electrons? Is that the question? Manganese.
Yes.
See, beta, you will only look at the oxidation state. Okay, what do we mean by oxidation state? Like how many electrons are participating, right? How many electrons are being given away or being gained? In this particular manganese tetroxide, sorry, now this is manganese permanganate, not tetra. Okay, that is for covalent. This is manganese permanganate. Okay, so here it is because it is bonded to 4 oxygen atoms. The 4 oxygen atoms are pulling the electrons more towards themselves, because remember, oxygen is more electronegative, and manganese is, by the way, a transition metal. So oxygen is pulling more electron away from it. It has a -1. This is a polyatomic anion. I should write it here. Okay. Here, this is manganese 2+ and with only 1. Okay, and this is ionic. This is also ionic. So this is the cation in this case, and this is the anion. Here, this is the cation, this is the anion. So can you see that so oxygen is pulling away. Here only 1 oxygen is pulling. Only 1 oxygen is pulling. Here 4 oxygen atoms are pulling away. So you can see there is less pulling here. So you can consider that as gain of electrons. Okay, but don't confuse yourself. Just understand that oxidation state has decreased. Okay, if you want to go into details, then this should be enough that there are more electrons being pulled away. Here, only one oxygen is pulling away. So pulling away is less here. So you can consider it as gain of electron. You can consider it. Okay, Yusra? And by the way, same story with carbon here. Same story with carbon. You can ask what's happening. How can you say that ethene is getting oxidized? Because if there's reduction, there must be oxidation. So yeah, this is oxidation. But if you think of it as just the gain of oxygen, that also is fine. But if you want to go into details, if you calculate the oxidation state of carbon and compare, then the oxidation state has increased here. It has increased. Okay. Okay. Yusra, are you somehow satisfied?
Yes, Miss, I understood.
Okay. Okay, let me see. Okay, let me just finish this off real quick. There's nothing, there's not much in here. Substitution reactions with halogens of alkanes, okay? Now, these substitution reactions require ultraviolet light in the form of sunlight for their initiation to get them started, okay? Photosynthesis is also a type of photochemical reaction, but it's completely different from this. That's completely different. But yes, that is also an example of photochemical reaction. By the way, what is a photochemical reaction? Any chemical reaction that occurs due to light energy, can be from the sun, and I think it can even be artificial. Okay, all you need is as much energy as ultraviolet light. Okay, so this energy breaks the chlorine-chlorine bond and turns them into individual atoms. Now remember, these are called free radicals. These are atoms, not ions. Why? Because if you count the number of electrons, there are still 7. Chlorine belongs to the 7th group. It should have 7 electrons in its outermost shell. So it has 7 electrons in its outermost shell. So these are neutral atoms. They are not ions, they are atoms. So we rarely come across them. But yes, in photochemical reactions, these are very common in photochemical reactions because somehow light breaks the bond in such a way that the atom separates with whatever electron it had when it was an atom. So it breaks the bonds and it turns them into individual atoms. They are highly unstable, of course. Why? Because they have the outermost shell is not complete. They don't like it. Okay, they have 7. They need just 1 more. That's why they formed this covalent bond. That's why they were in this form. So when light breaks it, they get back into this and they don't like it. They're highly reactive. They are waiting to combine with something else to get rid of this unstable state. They want to get stable again. So what they do is that I think the light, I'm not sure, but I think the light also breaks this bond, but I'm not sure about this. I was searching on it if the light breaks this bond as well, but I couldn't get the answer. So, but anyway, these chlorine atoms come and combine. They substitute. So this bond somehow breaks. And so now you have methyl free radical. They're called free radicals. These neutral atoms, they're called free radicals. So you have this methyl free radical meaning 1 electron is still unpaired and it is waiting. It is available to be paired. It is looking for a pair. So this chlorine atom comes and attaches to it and it becomes chloromethane. Chloromethane, and no need to count because there is only 1 carbon. So no need to count, chloromethane. And the hydrogen that was here, it goes and attaches to the other atom because that atom is also looking for a partner, right? So we have these 2 products, chloromethane and hydrogen chloride. Okay, and these are all gaseous in state. This is also in the form of fumes, gas. This is also gas, all are gases. Most of these hydrocarbons are gases, most of them, unless they are very big molecules. Okay, so, and then this is a chain reaction. So I have shown this in the cross dot and cross diagram. Hydrogen goes in bonds with the chlorine atom, and here you have. Now, if you keep supplying chlorine, and then more hydrogen atoms will be substituted and more chlorine atoms will come and attach. So first this hydrogen was replaced, then now this hydrogen also got replaced. Again, another hydrogen chloride. So this is like a chain reaction. It goes on, and it depends upon how much chlorine is available. And it also depends if the light is constantly falling because the light is responsible for breaking these bonds. So now how will we name this compound? This will be
Dichloromethane.
right. This will be dichloromethane. Again, no need to count. Okay. Then this process continues, and then the third hydrogen is also replaced. So now we have what?
Trichloromethane.
Yes, now we have trichloromethane, which is also chloroform, which in olden days was used as anesthetics. And so we have hydrogen chloride. Okay, now these are called haloalkanes, also called haloalkanes, halo from halogens and then alkanes. Okay, they are good organic solvents and they are used for dry cleaning. Why? See, especially in cleaning agents, when we want, like, for example, stain remover, you want a stain remover. These stain removers should be made up of such substance that can dissolve grease, especially grease. Most of the stains are greasy, not all of them, but most of them are greasy, like oil. So we want that grease to be dissolved so that we can easily remove them, right? So grease is also organic and it is non-polar. So it will dissolve in something which is non-polar and organic, because remember, like substances dissolve in each other. So in order to dissolve that grease, we need a non-polar organic solvent. So that is why they are very good. And then why couldn't we use a simple pure alkane? Why haloalkanes? Because on the other hand, I mean, though we do want the stain to be gone and we want the grease to be removed, but we also want the solvent to be little bit soluble in water so that it can be easily washed away. Otherwise, it itself might get stuck there. Okay, so we want something which is not that polar and not that non-polar, something in the middle, something in between, right? So they give us that. These haloalkanes are good for that purpose. So on one hand, they dissolve the grease, but on the other hand, they can be easily washed away with water. And so they're used in cleaning agents and for dry cleaning and all of that. And at the same time, they are also easily, they're volatile. They have very low boiling points. Why? Because they are non-polar. So they, dry cleaning, why is it called dry cleaning? Because there is no water involved. Organic solvent, you wash it and then it evaporates. At room temperature, it evaporates. Okay, another a point that I forgot to mention is that in all these reactions, you don't need water. You don't need water because all of them are non-polar and they can easily be carried out in oil, like for example, this bromination, hydrogenation, and the other reactions that we are going to come across. You don't need an aqueous medium. I mean, here, this is aqueous, but even if it were not aqueous, this would have still taken place. You don't need this aqueous. This could have been just pure bromine, and this would have still taken place. Okay, so I think I have covered the chemical reactions of alkenes and alkenes, but I could not cover the book questions. Do you find book questions hard?
No, miss.
They're easy. Okay, you can get you can get past paper questions if you want. We have done alkene and alkene reactions till bromination. Okay. Now hydrogenation and hydration are left, but there's not much in them. So inshallah, and then in the next class, which will be on Tuesday. Okay, I'll take next class on Tuesday. We will do the rest of the chapter and I will try to finish alcohols and organic acids. Inshallah, inshallah. Okay, is there any question?
No, miss.
Are you sure?
Yes, miss.
No question, miss.
Okay, are you guys able to do all the book questions? Is there any book question that you have problem with?
No, miss.
Okay, so get hold of past papers, worksheets, whatever. If you have any problem, share in the group, and inshallah, I will try to solve them. Okay, we'll solve them together.
Okay, miss.
Okay then. Assalamu alaikum wa rahmatullahi wa barakatuh.
Walaikum assalam. Allah Hafiz, miss.
Walaikum assalam. Allah Hafiz,
Allah
miss.
Hafiz. Allah Hafiz.
Allah Hafiz.
Have a
Allah
great day.
Hafiz. Allah Hafiz.